Hi, this is your cheat sheet to atoms. We'll be going over parts of the atom, isotopic symbols, atomic charge, models of the atom, average atomic mass, and relative abundance. So an atom, first defined by Democritus around 400-300 BC as the smallest indivisible particle of matter. Now this definition isn't exactly the most accurate, especially with the indivisible part, but it paints a picture of what an atom is. It's this unimaginably small building block that creates the entire universe as we know it. But then he died. And since then, we've found that there are even smaller parts to the atom. So the atom has a nucleus in the center, which is a lot smaller than this very inaccurate graphic that I have here, but bear with me. And the nucleus is made of two particles, protons, which are positively charged, and neutrons that have no charge. Changing the amount of protons changes what element the particle is. You probably know what elements are, but if you don't, they're fundamentally the basic building blocks of the universe. Sounds familiar to an atom because an atom is an element, basically. Different amounts of protons dictate what element the atom is. And to kind of illustrate that, I have a few Legos here. Trust me, okay? This is what we call a stud, this elevated piece of plastic. And you can think of this as your regular atom. Changing the number of studs in different orientations creates many different blocks that we can use to create whatever we can imagine. You can think of this as the number of protons changing, giving way to different elements. Changing the amount of neutrons in an atom changes the mass of that atom. And yes, although an atom and particles within the nucleus are incomprehensibly small, they do have some mass. And changing the mass creates isotopes, or mass variations of the original particle. Around the atom, outside of the nucleus, are electrons that erratically move in orbitals. And like I said, my graphic's a little inaccurate. They don't exactly go in these perfect orbits. Rather, they're kind of like very hyperactive kids just buzzing around their parents. It's a really weird picture, but it kind of paints what electrons kind of move like. Electrons are negatively charged, and so of course adding electrons will create a more negative charge, while removing electrons creates a more positive charge. Any change in the number of electrons from a neutral state of the atom creates what's called an ion of that element, a charged particle. Now, usually in a neutral atom of an element, it would have the same number of protons and electrons. All charges cancel each other out. If there are more electrons or protons, vice versa. More protons and or less electrons gives a positive net charge. Now, any element has multiple pieces of information that come with it, and a basic way to show that is with an isotopic symbol. X represents the symbol of the element, a short form for the element's name. A represents the mass number, which is the sum of the protons and the neutrons. And of course, like I said before, having different elements or having different isotopes of an element will change the mass number because it's changing each of these. B represents the atomic number of the element, which is just the number of protons. For example, here's hydrogen. Its symbol is H, and we have the mass number here. Hydrogen has one proton and one neutron. Adding that together gives us 2. And of course, the atomic number is just 1, since there's only one proton in hydrogen. Something to help you remember mass number and atomic number and whatnot is with the greatness of ape man. And no, I'm not talking about primates. This is just an acronym for 2 equations. First, we have A is equal to P, which is equal to E. This means that the atomic number is equal to the number of protons. This is always true no matter what element you have. In a neutral atom, number of electrons actually equals the number of protons, which is, of course, equal to the atomic number. And this won't be true if the element is an ion, the particle is an ion. Here, m, which is the mass number, is equal to the atomic number, which is, you already know, it's just the number of protons, and the number of neutrons. Now, when it comes to ions, the charge of the ion is denoted by a superscript, like this one here. To calculate the number of electrons of this ion, we would have to take the usual amount of electrons in a neutral state of this element and subtract the charge from it to get the number of electrons in this ion. In this case, a neutral atom of magnesium here has number of protons, 12. 12 protons. Subtract a charge of positive 2, and we get 10 electrons in this ion of magnesium, which makes sense. If it has 12 protons, and it's going to have less electrons than protons, since we know it has a positive charge. Now, let's go back in time to the good old days, and let's see how our view of the atom has drastically changed as time passed by. Starting with our guy Democritus. He thought that atoms were just really tiny particles, and the shape of the atom is based off the object it creates. For example, round balls are water particles, and sharp objects were fire particles, so on. It's a great start, but then fast forward a few centuries, and we have John Dalton, great guy, an English chemist who came up with Dalton's atomic theory, which kind of set the basis for our understanding of the atom. Because although inaccurate, it did help us get on our feet and slowly improve on it to come to where we are today. In short, he thought that the atom was just a solid sphere that was indivisible and followed the law of conservation of mass. Then, in 1897, at the turn of the century, J. Thomson, British physicist, found that there are negatively charged electrons around the atom. He believed that the atom was just a positively charged sphere with the electrons kind of sprinkled on top. Soon after, Ernest Rutherford, a New Zealand physicist, polished up Thomson's positive charged sphere as a nucleus that's at the center of the atom rather than this big ball. And of course, the electrons were just kind of orbiting the nucleus. But Rutherford thought they were just random orbitals. Then we have Niels Bohr, a Danish physicist who described the model of the atom that most people are familiar with. The electrons here are restricted to certain orbitals about the nucleus, kind of like planets around a star, which, like I told you earlier, isn't necessarily the most accurate. But it does show us the idea of orbitals, or kind of different areas that electrons tend to be. We won't be going over much of what orbitals are in detail, but that's kind of a short explanation of it. Finally, we shift our model completely, and as you can see, our diagram is completely changed to this gradient. This is thanks to Schrödinger and his discovery that electrons don't actually revolve around the nucleus like in Bohr's model. Rather, electrons exist in what is known as the electron cloud, or these kinds of 3D shaped orbitals, which represent the probability of finding an electron in a particular region around the nucleus. The darker the region, the more probable finding the electron. And as we go out, it's less probable to find an electron. And this comes with all the different fun quantum stuff that Mr. Schrödinger experimented and theorized about. You've probably heard of him from Schrödinger's cat, very famous thought experiment. Now, orbitals are still here. However, rather than being rings around the nucleus, they're kind of different shapes of clouds. So they do exist, it's just in a different way than we originally thought. Okay, let's shift gears back to kind of a mathy part of atoms with the atomic mass, the mass of the atom, or in this case, the mass of 1 mole of an element. which is often given in atomic mass units, AMU. For the purposes of this video, we'll just say a mole is kind of like a unit, or just a set standardized number of atoms. Now, the atomic mass, like I said, is primarily determined by the combined masses of the number of protons and neutrons. However, there are different variations to atoms in our world, with multiple different isotopes, like I had said before, of a given element. If there are multiple, then how can we coin a specific mass to an element? Then we would have to take an average, or rather, a weighted average of every isotope. That is, in any given sample, there's always going to be a set amount of each type of isotope. They're not going to be uniform. Well, like, for example, let's just say 10% of one type of isotope, 40% of another isotope, so on. So we need to take in consideration the abundance of each isotope, how much there are of each. How are we going to do that? Using what we call relative abundance, or percent abundance, which is a percent showcasing how much of a specific isotope exists in all types of isotopes of an element. And I just have to take the number of atoms of all the elements, divide it by the number of atoms for a specific isotope, multiply that by 100 to get the percent. Then to find your average atomic mass, you take the sum of all the isotope masses times their relative abundance. Pretty simple, but I do recommend, of course, doing practice problems to find average atomic masses and whatnot. Again, chemistry is a lot, not just about learning the concepts, but also being able to do the math that comes along with it. Thanks for watching. If you have a specific topic you'd like me to go over, make sure to write it in the comments, and I'll see you in the next cheat sheet.